Welcome, students, to today's Explainer on Database Design. If you're studying software engineering, you've probably already figured out that writing code is really only half the battle, right? Today, we're focusing on the architect's blueprint for building a database. We're looking at Chapter 9, which lays down the absolute foundation of how information systems are structured, conceptualized, and eventually brought to life. Okay, let's dive straight into this. Here is our 6-part syllabus for today. 1. Introduction and life cycles. 2. Phase 1, the initial study. 3. Phase 2, database design. 4. Implementation to maintenance. 5. Design strategies. And finally, number 6, an exam review. Section 1, Introduction and System Life Cycles. Now, before we draw a single table, we really have to adopt the right mindset. Information systems, they don't just happen by accident. They are the product of an incredibly carefully staged development process. And the golden rule here is this: a database is not an end in itself, it is a means to an end. It exists solely to solve a business problem. They're meticulously planned out to serve specific organizational goals. Basically, if the business doesn't actually need it to solve a problem, well, we shouldn't be building it. So to understand how we build these solutions, we first need to define the SDLC, or the Systems Development Lifecycle. The SDLC is the continuous, iterative process of creation, maintenance, enhancement, and replacement of an entire information system. Think of the SDLC as the big picture. It traces the history and development of the entire application program. And notice that word iterative. It means we constantly refine it over time. It's a continuous loop, not just a straight line from start to finish. Now, nested right within that massive SDLC is the DBLC, the Database Life Cycle. By definition, the DBLC is the specific cycle tracing the history of the database within the broader information system. So if the SDLC is the whole house, the DBLC is the plumbing system inside it. And just like the broader software system, this database lifecycle is highly iterative and repetitive over time. We build it, we test it, we refine it, and eventually we replace it. Let's walk through the 6 overarching phases of the DBLC just to give you a mental map of what we're covering today. Step 1 is the initial study. 2 is database design. 3 is implementation and loading. 4 is testing and evaluation. 5 is operation. And 6 is maintenance and evolution. So, briefly recapping before we move forward. The SDLC covers the entire software program, while the DBLC is our 6-step journey specifically for the database. And remember, both continuously loop and evolve. Section 2, DBLC Phase 1, Initial Study. This is where the really vital detective work happens. The initial study focuses on analyzing the company's situation, defining the boundaries, and establishing strict business rules. So how do we actually do this? Well, by interviewing end users. This is an absolutely critical step because you have to separate mere wants from actual business needs. A super common mistake junior software engineers make is treating the symptoms rather than the root source of a problem. Like, if users complain that a report is slow, a symptom might be a slow SQL query, but the actual root cause might be a fundamentally flawed data structure. We fix that root here by properly analyzing the real boundaries of the project. Section 3, DBLC Phase 2, Database Design. Database design is the absolute core of the database lifecycle. It's where the actual architecture of your system is conceptualized. When we map this out, you'll see database design isn't just one single step. It's broken down into conceptual design, DBMS selection, logical design, and physical design. We literally move from a high-level, hardware-independent view all the way down to the nitty-gritty, hardware-dependent storage details. Let's unpack these layers one by one because they're absolutely crucial to understand. First up, we have conceptual design. This is defined as a hardware and software independent blueprint of the database structure representing real-world objects. In simple terms, this is how the end user views the data. We use entity relationship diagrams here to map out things like customers, orders, and products. At this stage, we genuinely do not care if we're using Oracle, SQL Server, or a cloud service. We are entirely independent of the physical hardware and the database software. Once we actually select our database software, we move to logical design. This is defined as mapping the conceptual design to a specific DBMS model, such as a relational database. Here, we translate that abstract blueprint into specific technical constructs. We define the actual tables, the columns, primary keys, and foreign key constraints. We're now software dependent, meaning we're designing specifically for a relational model, but crucially, we are still hardware independent. Finally, we hit physical design. The definition here is mapping the hardware-dependent data storage organization and access characteristics. Now we're finally getting our hands dirty with the physical hardware. We determine exactly how the data will be stored on disks, set up security measures, and configure performance parameters. So for a really quick mini recap of these three stages, conceptual design is for the business, logical design maps it to the relational software, and physical design maps it to the actual hardware. Section 4. Implementation, testing, and maintenance. Now that our blueprint is complete, we enter the final phases of the DBLC, where the database is actually built, tested, and put to work in the real world. Phase 3 is implementation and loading, where we finally create the tables and load the data. Now, a massive modern shift here is virtualization. Virtualization is defined as creating logical representations of computing resources independent of physical hardware, very often via SaaS or software as a service cloud databases. Instead of buying clunky physical servers, we use cloud platforms like Microsoft Azure or Amazon RDS. This radically modernizes implementation because it allows us to spin up, scale, and manage databases instantly without ever touching a physical server. Moving right along to Phase 4, testing and evaluation. A major part of this phase is ensuring our data is actually protected and recoverable. We do this through three main types of backups. A full backup is exactly what it sounds like, a complete copy of the entire database. A differential backup only copies the objects that have been modified since the last full backup, which saves a ton of time and storage space. And finally, a transaction log backup only backs up the specific operations recorded in the log that aren't in previous backups. Understanding the stark contrast between these three is vital for ensuring total data recoverability. After Phase 5, which is simply the day-to-day operation of the database, we reach Phase 6, maintenance and evolution. And guys, this is by far the longest phase of the database lifecycle. Maintenance generally comes in three flavors. First, corrective maintenance, which just means fixing bugs. Then, adaptive maintenance, which involves adjusting the database to new business changes. And lastly, perfective maintenance, where we enhance performance, maybe by adding indexes to speed up queries. To recap these final phases, we implement the database, often using cloud virtualization, we rigorously test and back it up, and then we spend the rest of its life maintaining and perfecting it. Section 5. Key Database Design Strategies. Okay, now that we've traced the entire life cycle, let's explore the classical approaches to structuring database design. Pay close attention here, as these are foundational, highly testable concepts for your upcoming exams. When designing a conceptual model, you generally choose between two paths. Top-down design starts from the macro level. You begin by identifying the broad, main entities, like a university or a department, and then you break them down into specific attributes, like department name or location. Bottom-up design is the exact opposite. You start at the micro level with a massive pile of raw attributes, like student ID, course code, professor name, and you logically group them together to form your entities. Another absolutely critical choice is centralized versus decentralized design. Centralized design is typical for simpler systems. It's where one small team, or maybe even a single database administrator, designs the whole system from start to finish. Decentralized design, however, is completely necessary for massive corporations. Here, multiple teams work independently on specific modules, say one team on human resources, another on sales, and those modules are later aggregated into one massive conceptual model. So, in summary, top-down starts big and goes small, bottom-up starts small and builds big. Centralized uses one team, decentralized divides and conquers. Section 6. Summary and Exam Review. Understanding how all these pieces fit together is really what separates a coder from a true software engineer. Let's lock in what you've learned today with an ultimate study guide table. Let's walk through it. First, the life cycles. Remember, the SDLC manages the whole software program, while the DBLC is specifically for the database. Both are continuous and iterative. Second, database design stages. Conceptual is hardware independent for the user. Logical translates it to the relational software model. And physical is hardware dependent for disk storage. Third, backups. Full is everything. Differential is only changes since the last full backup. And log captures specific transaction operations. Finally, design strategies. Top-down moves from entities to attributes, and centralized uses a single design team. Memorize this, and you will be in fantastic shape for your tests. I want to leave you with a final, slightly provocative thought to ponder. As we established with the life cycles, a database is never truly finished due to its continuous evolution and daily operation, right? So with millions of updates constantly changing the data, how do we ensure two users don't overwrite each other's work at the exact same millisecond? If the database is constantly moving, how on earth do we protect its integrity? Well, that exact question leads us directly into our next major software engineering topic, transaction management and concurrency control. Thank you so much for joining me for this explainer, and I will see you in the next one.